In this tutorial, we're going to talk about energy conservation. Specifically, we're going to look at how Cycles handles incoming energy on surfaces that contain a diffuse and a glossy component. And I'm going to show you why the default principled BSDF shader, most often used for this purpose, isn't producing proper energy managed results. Modern renderers use a framework for handling light at the material level referred to as energy conservation. Energy conservation refers to a simple fact that a material can't or shouldn't reflect more light than what comes into that surface. This makes sure these surfaces look as real as possible. But Cycles isn't doing this properly, and as a result, it can impact the realism of your scene. The most impacted types of surfaces are generally shiny, low roughness ones like porcelains, plastics, or any other material that contains multiple scattering layers, including car paint, where light has to interact with multiple layers on a surface. Car paint is something we're going to discuss a little bit later on in this tutorial. Let's take a look at this file right here. And then we're going to take a look at a couple of other renderings in order to sort of get a sense for what it is that I'm talking about. If we look at this rendering, this scene right here is what Blender and Cycles have rendered by default. The rendering doesn't look bad. It looks like sort of a product shot. But there are a couple of things that I want to draw your eye to. We have light coming from a lot of different directions, and we have a little bit of directional light, which we can see here, a little bit of shadow over here. But when I look at these bowls, they look relatively flat. And what I'm seeing with my eye, because I have sort of a trained eye to this, is the fact that we are reflecting too much light in some areas. As soon as I switch to a correct energy managed layer, this is what we get. And it may seem a little bit subtle, but what you can see is that we have greater curvature to the surface. And I've got these black and white bars back here to help us see the reflected difference in light and dark. And at these higher glancing angles, we need to see that. If I turn off the energy managed version again, you can see it looks like it's too bright along the edge. When we look at the same scene from a higher camera vantage point, we can clearly see that the bowl has glowiness around it. It's sort of flat in its shading, and at this high incidence angle, we should definitely be seeing more contrast on the front of the porcelain mug. We can also see on the blue tumbler, it seems flat too. So let me turn on proper energy management, and now we can clearly see the correct light reflectance and distribution on our objects. Let me pull up one more scene that we're going to examine. In this rendering, this is by default what Blender has rendered for us. We've got a countertop that's got a specular component to it sitting on top of the base color, which is a diffuse component, and at this glancing angle, with the camera low down to that surface, it's highly reflective. We also have this cabinet wood right here that looks a little bit too bright. It's the exact same material right here with this face-on facing wood. Something isn't quite right about that. So let me turn on the properly energy managed version so you can see what's going on. When I turn that on, notice that the glowiness disappears here. This is because at this higher glancing angle, the varnish that sits on top of this wood, which has its own reflectance layer, is no longer reflecting too much light, and it looks like it matches over here. In this example, we can see this red teapot and the white porcelain mug are particularly interesting examples, because sometimes you're actually going to have a darkening at the edge or at high glancing angles, especially if the background is kind of dark. And in this particular case, we can see that the teapot is kind of somewhat flat shading. We can see at the high glancing angles, it's about the same shading as other parts, and this isn't quite right. In the white porcelain mug right here, the edge is a little bit too flat. It should round slightly and reflect with a very hint of red, a little bit more of this red teapot in the background. So let me turn on the properly energy conserved version, and look what happens. It suddenly becomes more dynamic, even if in a subtle way. We can see at these high glancing angles, it darkens slightly, making room for the reflections that are there. And in fact, in the white porcelain right here, there's a slight gradient, and we see a hint of the red from the teapot. In fact, in the top, we also see very hints of darkening, which is consistent with what the Fresnel effect would do under some circumstances. So when we look at these examples, it may seem subtle, but the surfaces are reflecting more light than has actually come into those surfaces, and in some cases it can result in these surfaces looking too bright or flat without the curvature definition we'd expect. So the key material properties we want to understand in order to grasp the energy conservation problem are diffuse, specular, and the Fresnel effect, or the Fresnel curve. We'll also look at clearcoat and subsurface scattering as secondary properties that are also affected by energy conservation. So let's take a look at the user interface here for a minute and just understand which components we're talking about. We're talking about the base color, and we're talking about the specular component. These are the two primary components that we're going to be talking about. We're also going to be talking a little bit about roughness. Let's talk about base color for a second. Base color is the diffuse component of a material, and diffuse scatters light basically in all directions. It really doesn't matter too much what the view angle is. It's really useful as a standalone material component for things like concrete, dirt, a brick wall, old unglazed pottery, wood surfaces without any kind of varnish or coating, or any surface that just looks really rough. We can think of it in graph terms by this simple horizontal line. Specular is the glossy upper material layer we often just call reflections. Specular reflections can be very sharply reflective, or they can be a little bit more rough. Let's talk about the Fresnel curve now. There isn't a direct location where you control the Fresnel curve in the principled BSDF. It's actually controlled by setting the specular value, which sets the low incident end of the Fresnel curve. In most 3D applications, the user sets the index of refraction to control that. But in Blender, IOR simply controls the Fresnel effect as it governs the transmission channel. The Fresnel curve governs the expression of the glossy specular layer. The Fresnel effect simply says that at low incidence angles, you have low reflectivity, and at high incidence angles, you have high reflectivity. The index of refraction controls the intensity of the Fresnel curve, and an index of refraction of 1.52 is the most commonly used value for many surfaces that have low face-on reflectivity and high glancing angle reflectivity. But Blender doesn't ask the user to input an IOR value to control the Fresnel curve. It asks the user to put in an equivalent low incidence reflection value. The equivalent of 1.52 is a specular value of 0.425. So these two channels interact with each other via the Fresnel curve, and it's this interaction that's central to our understanding of the energy conservation problem. This chart represents the total amount of light energy coming into our objects, in this case all illuminating the diffuse base color channel. But when we turn on reflections, which I've added not only to the spheres, but also to the ground object, Cycles simply adds the specular light intensity on top of the existing diffuse energy. The diffuse layer is receiving the same amount of light as if there was no specular layer enabled. There's no compensation. You can see the ground becomes glowy, as do the edges of the spheres. So this is the problem right here. This is what Cycles is currently doing. So what we actually need is something that will actually compensate for the energy that is no longer going to be available to transmit down to the underlying base color layer. And what we should end up with is something like this, where there's a little bit of darkening happening at those glancing angles to allow for balanced energy between the diffuse and specular layers that is most apparent at higher incidence angles. So for instance, if your view incidence angle is 10 degrees, 4.25% of incoming light reflects off the specular layer, and 95.75% of the remaining light then illuminates the diffuse layer. At a higher glancing angle of 75 degrees, 26% of light reflects off the specular layer, and 74% of incoming light then reflects off the diffuse layer. That is a balanced energy system. So let's finally take a look at what the node setup is like. I've created a very simple demonstration scene right here that has these slabs, and with our line of sight relative to those surfaces, we have a pretty high incidence angle, so the surfaces of these slabs at the top should be pretty reflective. If we look at the white slab right here, I've got my base color, which is the diffuse component, and then I also have the specular turned on to that 0.425 value that we've talked about. Roughness is pretty low at 0.1, but we still don't see a lot of reflections on there. And the top of the slab is also kind of glowy. There's that term I'm using again. So what we need to do to make it correctly energy balance is add two nodes. We're going to come over to add, and we're going to add Fresnel. Drop that right there. And the second one that we're going to add is Mix RGB. Color 1 will be our primary color. That will be the color that governs low glancing angles, sort of the face-on look, the primary color of your object. Color 2 is going to be your edge reflectance. It's going to be the counterbalancing color. So we come over and make sure that the Fresnel is 1.52. That will match what we have in the specular. Take Fresnel and drive the factor, and then what you do is you just come over to the color that you're using in the principled BSDF, copy that value, and then just paste it in. For the second color, you can usually just drive that to black. So then we just drive this over to base color and watch what happens. So now you look at this and it's not quite glowy anymore. And it becomes a little bit darker to the back because we have this black checkered background. Let's do this now to the other ones. In fact, what I'm going to do to make this easy is I'm just going to copy those and I'll paste those here, grab my base color, copy that, paste the hex code in here. That already drives to black, and then we just take this to base color. And that is now correctly energy managed, and we'll do the final for the gold one. Copy, paste, and then drive that. So these have somewhat lower incidence angles. This is the one that's most prominent. So this back darker checker background that I created, I put that back there to help show that this should actually be darkening. And we're going to take a look at a couple of photos that I took the other day that exactly demonstrate this in the real world. If I actually took this checkered background right here and I changed this to the same one that I'm using right here, then we can also sort of examine this from a different angle. So I'm going to come down here and I'm going to change to light checkers, and it really changes the dynamic of it. It's fascinating. But watch what happens if I come back over here now to this top slab and I remove our two energy conserving nodes. Look how bright that top gets. That's by default what Blender is doing. But by adding these two nodes in right here, we can energy conserve it and it looks just more natural. I was at a coffee shop recently that had this countertop that really demonstrated this effect really nicely. As my line of sight is fairly high up looking down onto it, we can clearly see that it's quite a white surface. It's very reflective, it's very white. We can see the reflections of everything above it. But watch what happens when I move the camera down closer to the surface so that I have a higher incidence angle relative to it. Do you see how it's become darkened up? So here's a test using subsurface scattering. In this particular case, I've got this table that has a marble on top that has a little bit of subsurface scattering on it, which we would kind of expect from a marble. So we have a lot of light interacting with the surface that's not only bouncing off of it in two locations, at the diffuse level, at the specular level, but is also interacting into the surface using subsurface scattering. We can see in the material setup that I am using a bitmap right here, this marble, and driving both the base color and the subsurface color with it. We have a specular of that 0.425. So let's take a look at what this looks like when we change it. So this is without any of the counterbalancing that we're doing, and I'm going to look at this at the high level, which means that we've got a low incidence angle relative to our camera, so we wouldn't expect too much of an effect here. But when we come down and look at the low camera angle relative to the surface, it looks kind of glowy and overly bright. And the illumination looks just a little bit flat. So when we come back over here, we need to produce our manual counterbalancing, energy balancing setup. But it's a little bit different here because this case, we're using bitmaps as opposed to just a simple color. But the process is still the same. So I have set up over on the side over here. I've got the components already set up. And let's take a look. We have our Fresnel node, and we have the Mix RGB node right here. Instead of using colors, we're going to use the two bitmaps. And what I've done is I've taken this basic lighter marble bitmap, and then I've produced a darkened version of it for our counterbalancing color, our glancing angle color. So what I need to do is just configure these really quick. I'm going to uncouple these here, move this over. This comes to become our top color, color number 1, and then the darkened version becomes color number 2, which functions for glancing angles. And then we want to make sure our Fresnel is set to 1.52. And then we tie this into both base color and subsurface color. So we're going to need to attenuate the subsurface amount in the same way that we're attenuating the base color. So this is without our manual setup, and this is what happens when we turn that on, is that it darkens up that glancing angle so it correctly balances the amount of energy coming into that surface. And it looks more real. It looks more three-dimensional. Final thing that we're going to take a look at right here is something that you could use for, say, a car paint. In this particular case, I have this product that had an anodized metal case that had a glossiness on top of it, sort of a coating if you want. The principled shader has a clear coat function, but I'm going to show you why it's also not properly energy managed and how you can use an alternate version to get that. So let's jump over to Blender right here, and we can take a look at this basic scene that has that setup. So the material has the base color, and we have it set to metallic mode, and then the roughness is set to 0.47, nearly 0.5. So it's fairly rough. And when we do that, we get this basic appearance when I'm rendering these products. When we want to add the coating on top, we would simply come over to Blender, adjust the clear coat. Now let me talk for just a second about clear coat and specular in relation to each other. They're both essentially top coats, if you want to think about that, on top of the base color. And the specular function behaves a little bit differently in metallic mode. So for right now, I've simply got it set to 0. We are wanting to add a coating on top of this metallic blue. And it's calibrated differently value-wise than the specular is. We've been using a value of 0.425, which is 4.25% reflectivity at low incidence. Think right here at the center of the sphere. And the clear coat is calibrated by a factor of 10 different. So if we want 4.25% reflectivity of the coating, we simply type in 4.25, right? So I don't know why they're calibrating the two values differently. And you can see that it produces this coating effect on top of the metal. And if we come back over to our photo and we look at the effect of simply adding the clear coat, in this case I've used actually a value of 3. If I turn it off, and then turn it on again, we see the appearance of that coating, but we don't see anything happen to this underlying metallic blue color. And it should be counterbalancing that just a little bit, especially at higher incidence angles. So let's come over here and really emphasize this. I'm going to turn on a clear coat of 25%, which makes the coating look really quite bright. But again, when we look at that versus the original, nothing happens to the underlying blue color. And that tells me that it's simply taking those coating values, reflectance values, and adding them on top of the metallic base color. And that's not quite physically correct. So what I'm going to do is I'm going to show you how we can come back over to Blender. And we can do this in two ways. We can use this Fresnel plus Mix RGB setup that we've done. So that's one way. But there's actually even a little bit better way that you can be used for car paints. And I happen to have a node set up already over here, and I'm going to pull this over and we're going to examine this here pretty quickly. So I'm going to uncouple this and I'm going to come over, and the first thing that we're going to do is we're just going to look at this. We have a glossy BSDF, and then we simply have a duplicate of the principled shader that we were just using right here. So it's got the base color, we're set to metallic mode, and roughness is pretty close. I'll put that to the 0.46, so it's pretty close. And we're not using a coating. Instead, what we're going to do is we're going to mix it against a glossy BSDF. Now, when this is in the bottom shader slot, it actually sits on top. I don't know why it's inverted this way, but that's the way it is. I want to examine what this glossy BSDF does to these components all by itself. So what I'm going to do is drag it and hook it up to the material output. And we're going to see that it creates like a chrome, a mirror type of surface. It's a white color and it has very, very small roughness. And so it creates essentially a perfect chrome material. But what I want to happen is have the Fresnel node right here function as a mask to transition between this, and it will create a top coating type of effect. So when I come over here and tie this back in, then we get this. Now, the benefit of what is happening right here is it actually balances the energy between the two as the Fresnel node transitions from one to the next. And that's the benefit. So let me just show you how that actually plays out in our final rendering. And I'm going to turn on this manual construction. And what I want to bring your eyes' attention to is what's happening back here at these higher glancing angles. Let me turn it off, and then let me turn it back on. And you can see that it's correctly darkening the higher glancing angle parts as we increase reflectance. And as I said earlier, what that may mean in some cases is part of your surface may darken in order to make room for this coating light using this manual setup. But to really emphasize this point, what I'm going to do is if I were to come over and take this index of refraction up to a value of 3, that's going to really affect the strength of the top coat. Because what the index of refraction does is as it increases the strength of the coating at low incidence angles, which is basically making it look overall more prominent on the surface. But it's also correctly balancing the energy distribution to the underlying material, to this underlying base coat, and darkening it correctly. So when we take a look at an index of refraction of 3 on that Fresnel node, it correctly darkens the underlying surface. So let me turn this off, compared it to the no coating version, and then back to version 3.0 for the index of refraction. We get that, and it correctly darkens the underlying surface, and it counterbalances the two. So if you're going to be using a car paint type of setup, this is actually a better way to do it, using this setup right here. A Fresnel node going into a mix shader with this glossy BSDF, and then your shader set to metallic mode, and no coating. The final thing that we need to talk about is roughness as it relates to the Fresnel effect in cycles. So when we look at the user interface right here, we can clearly see that roughness is one of the main parameters down here. Generally, you can use this node-based approach if your roughness is at 0.3 or less. As roughness increases, the Fresnel effect decreases, meaning at glancing angles, reflections become softer and less pronounced, closer to what you'll see at low incidence face-on angles. This is a function of the GGX microfacet scattering system, but it doesn't equally attenuate the Fresnel effect generated from the Fresnel node. So the node-based energy conservation technique will not work right at higher roughness values. This isn't a big deal though, since the strength of the Fresnel effect decreases with increasing roughness. So I hope you found this to be a useful tutorial. I know this is a little bit of a more complex subject, but it can help produce better renders for you.